Welcome back, everyone, to the One World Minds seminar. I'm really happy to be introducing my colleague, Daniel Kane. Daniel has a really wide range of interests spanning a bunch of areas in math and a bunch of areas in computer science. He's done work in number theory and combinatorics. He's done work in de-randomization, on Boolean functions and machine learning, and recently he's been interested and doing work on computational statistics. If you don't believe me, you should take a look at his webpage and publication list. It's really impressive how many things he manages to work on. So with that, I'll give the floor to Daniel.
Hey, thanks for the introduction. So I'd like to talk to you all today about point location and active learning and how to learn learning half spaces almost optimally. This is joint work with my collaborators, Max Hopkins, Shachar Lovett, and Gaurav Mahajan. In any case, as we sort of were talking about before, this talk I think is a little bit short, so if you want to ask questions, feel free to, since without them we'll probably end early. In any case, to get started, so the first thing I'd like to talk about is the point location problem. And the basic setup here is that you're given n hyperplanes in R to the d, and this splits space into a bunch of regions. This is a hyperplane arrangement that splits space into regions like this, splits into a bunch of cells. And you're given some unknown point x in RD, and your goal is to determine which region it's in. And so, this point is in that, shaded region there. And the query model that we allow is you're allowed to make linear queries. So you could, for example, pick that red half space, hyperplane, and you get told which side of the hyperplane the point is on. So, it's on the top half, and then you ask about this one and find that, the point must be somewhere in this cone, and then that one, you find the point is in that triangle, and you query the last half space, and you've successfully narrowed it down to the correct region. Now, one slight note here that's useful in at least some of these versions of the problems is that we'll actually allow you to query hyperplanes that don't necessarily need to be sort of the defining hyperplanes of this arrangement. So I could ask my first question to be, say, this hyperplane. I just invent a new one and determine that the point I'm looking for is over there. And maybe if I make the right guess, I can actually, with just 3 guesses, pin it down to my point has to be somewhere in this triangle, which is contained within only one cell. And so I'll actually have the answer perhaps faster by making these queries via other hyperplanes that were not in my original set. And maybe a little bit more formally, the model that I'm allowing myself is a linear decision tree. So what I get to do is I get to pick any affine linear function that I like, and I get to ask the question, is L of x bigger than, less than, or equal to 0? And so I get some answer to that, and based on the answer that I got to that question, I then get to pick some other function, and again, ask bigger than, less than, or equal to 0, and I keep on going like this, and the total sort of cost of this procedure is the number of these questions that I have to ask before I figure out what region my point is in. Now, to simplify things a little bit, I'm going to assume throughout this talk that all of the hyperplanes that we have are homogeneous. They pass through the origin. And if I'm willing to increase the dimension of my problem by 1, this is actually without loss of generality, because I can just add 1 extra coordinate where all my points have 1 in that coordinate, and that can sort of give me the constants. And so this is without loss of generality, but it simplifies things a little bit, because now my hyperplane is defined by just listing a single normal vector h rather than listing, a normal vector h and a threshold t or something like that. And so this just simplifies the representation of everything a little bit. So to formally specify the problem, what I have is I have a known list of hyperplanes defined by these normal vectors h1 through hn in Rd. And I have an unknown point x in Rd. And what I'd like to determine is I want to determine what cell x is in. And what that means is that for every hyperplane in this list, I need to know which side of the hyperplane x is on. So I need to determine the values of the signs of hi dot x for all I going from 1 to n. So that's what I want to determine. The types of queries that I'm allowed to perform are I can pick any hyperplane normal vector h, and I can query to get the sign of h dot x. And the question is, how many queries are necessary to answer this problem? Okay, are there any questions about this?
Quick question. Can you go over how, assuming the hyperplanes pass through the origin is equivalent? I didn't really understand why that would be the same.
Right. So the basic point is that if I add one dimension, and to every query point, I just add, like to every point, I add an extra coordinate, which is 1. Then sort of affine, I'm basically putting all the points in my original problem on some plane that doesn't pass through the origin. And then any affine hyperplane that I want in that d-dimensional subspace, I can get as the intersection of a plane that passes through the origin. I'm basically using projective coordinates, and by adding one extra coordinate, I can simulate affine things as well.
Thanks.
Sure. Are there other questions?
Seems not now. People should feel free to enter questions in the chat or interrupt the speaker at will. And Rand and I can handle any chat questions, Daniel, so you don't have to worry about that.
Okay, sounds good. Okay, so yeah, so this is the point location problem. And now we're going to change gears for a bit and talk about another problem that comes from sort of a pretty different area, and that's active learning. And so what's the basic idea here? In machine learning, one of the basic problems that you have is that you're given a few sample values from an unknown Boolean function, and you want to learn the function. And I mean, this function might be, something practical like, we've got pictures that are either cat or dog pictures, and you want to determine which one's which. And so what you get is, you can sample the function at a bunch of points. You have, all of these points, and some of them have red values and some of them have green values. And you want to be able to predict what the function is everywhere. Now, of course, in general, if it's just a random function, this is impossible. But functions that show up in the real world tend to be at least somewhat nice. And so if you assume that the function is nice, is from some nice class, and we're going to work with the very simple class of a linear threshold function, then often you can do it. So, here you've got these points. You note that there is some hyperplane that separates all the red points from the green points. So at very least, the observed function is consistent with the following linear threshold function. And there are questions that you can ask, which is a little bit beyond what we're going to discuss about generalization, like how many points do you need until the hyperplane that you find actually will give you good results on points that you haven't seen. But if all you want to do is you want to find some hyperplane that's consistent with all the values that you've seen, that's reasonably easy to do. That's just a linear program. Each point gives you some set of linear conditions on the coefficients of the hyperplane, and you just need to solve that. So active learning is a sort of modification of this that comes out of the idea that sometimes getting labeled examples of your function is expensive. And I mean, you can imagine that, if you want unlabeled examples, if you just want, pictures that may or may not contain a cat in them, that's really easy to gather a large data set. You just go online and scrape the internet for pictures. Whereas if you want to be able to label those examples, if you want to know which ones of them actually have cats in them or not, well, unless you already had a good algorithm for classifying, you'd probably need to go and ask a human. You know, you'd have to take a human and have them spend a lot of time telling your algorithm which pictures have cats and which ones don't. And it might be even worse than that if, say, you want to be able to algorithmically identify, you know, which X-rays correspond to patients that probably have cancer, because then you can't just pick any human to label things. You need someone who's actually a domain expert in the area. Their time might be more valuable. And so often finding labeled examples for your algorithm is much more expensive than getting lots of unlabeled ones. And so active learning is sort of a model that reflects this. What your algorithm is given is it's given a very large pool of unlabeled examples that, you know, it's scraped off the internet. And then if it wants to learn the labels, the algorithm can query. So the algorithm can say, and in particular, the algorithm can try and do this adaptively. It can try and find the examples that are sort of most representative or most informative. And the hope is that by sort of cleverly picking which examples to query, we can do much better than just having to label the entire pool of examples. And one modification that I will make to this is that sometimes you might allow the algorithm even to synthesize examples and ask questions about those. And I mean, there are a number of practical cases where maybe synthesis isn't sensible, but some may be where it is. And for the sake of, you know, being an interesting mathematical problem, we'll probably work with the latter model, where you can synthesize examples and ask for queries, even if those points were not in your original pool. Finally, the goal of this very often is, well, I mean, you can't expect to learn the full function on all examples exactly, but maybe you could hope to learn what the function is on every example in your original pool. So you're given a big pool, you can query the value of the function at various places, and you'd at least like to learn what the true labels of the function are on every example in your original pool. Are there any questions about this?
There's a question in the chat. It says, what properties are you assuming about the unknown points, the point from the input space? I don't know.
What properties are we assuming about the unknown points? So for most of what we're doing, we're actually not going to make sort of any assumptions about what the pool of points are. You'll have to make some assumptions about what the functions are, and we're generally going to assume that they're half spaces here. But a lot of the interest in what we're doing here is we really do not want to make any assumptions at all about what the points in your pool are. And okay, so just to go over a quick example here, so we have a pool of points here, and we can query. So that point over there, we learn the value of the function there is green, the value of the function here is red, the value of the function there is green, the value there is red. Maybe we even synthesize a new point over there and find that the value is green. And eventually, maybe since we were told that the red and green points are separated by a half space, we have enough information to determine that, maybe this doesn't have to be the exact half space, but hopefully we know that whatever half space it is, it classifies all of the remaining points in the following way. And so the goal is just to get enough information about the true half space that we can correctly classify all of the remaining points in our pool. Okay, so
Sorry, so Daniel, we have
Yeah.
one question from the audience. Rishikesh Maskar is asking, how can you do anything without assuming, for example, that the classes are disjoint or well separated?
Sorry, I'm not sure what classes. So we need to assume
red and green in this
the
case.
red and green. So yeah, we'll get into that. If you assume that they are separated or well separated, things become much, much easier. But yeah, I mean, we're going to get into this. We actually can, at least in this sort of simple model, do things even if things are arbitrarily badly separated.
Great.
And you have to do something that sort of takes into account when things are badly separated. You need to be able to notice that and take advantage of it. In any case, so let's look at a formal specification of this problem. So we have a known pool of points, x1 through xn in Rd. And there's an unknown separating hyperplane. Again, we're going to assume that it's homogeneous. And again, up to changing the dimension by 1, this is without loss of generality. So we have this unknown hyperplane H. And what we'd like to determine is we'd like to determine for every point what side of the hyperplane it's on. So we want to determine the sign of H dot xi for all I going from 1 to n. And the queries that we can perform is we can pick any point x in Rd we like, and we can learn the sign of H dot x. And the goal, of course, is, how many queries are necessary to learn the correct classification on all of our points. So that's the active learning problem. We've talked about point location and active learning. Why are these in the same talk? Well, there's actually a duality between these. These problems are actually formally equivalent to each other. I mean, if you just take every h and replace it with an x, and take every x and replace it with an h, you find out that these two problems, as I've specified them, are really the same problem. The only real difference here is how we're thinking about them. You can think of the things that you are given as points and you're trying to learn a hyperplane, or you can think of the things that you are given as hyperplanes and you're trying to learn a point. But these are dual to each other, dual notions, and therefore, in some sense, these are actually just the same problem, which is pretty cool that, these two problems that have sort of a very different flavor to them turn out to be equivalent. And so the goal for the rest of this talk is we would like to try and resolve the question of the complexity of these two problems, how many queries are needed. And for basically the rest of the talk, we will take the point of view of active learning. Because I think at least that it's a little bit easier to work with. It's more intuitive to think of the things that you are trying to learn as points, as the values of a function on points, than it is to think of them as hyperplanes that you're trying to find, what side of them things are on. But I mean, of course, the math doesn't matter. This just seems, I think, it's useful for intuition. Okay, so that's the problem that we are trying to solve. And before we get into it, let's try and talk a little bit about what's known. And to start off, we can look at easy upper and lower bounds. And so the easy upper bound, the easy algorithm is you just, you test every single hyperplane, or equivalently, you test every single point in your pool. And if you've got, n hyperplanes in d dimensions, this is n queries, and it very naturally gives you exactly the information that you need. Lower bounds are at least a little bit more difficult, but there's a pretty easy one coming from information theory. In particular, no matter what queries you make, whether they're in your pool or not, you can only get O of 1 bits of information per query. The only answers you can get are, the dot product is positive, negative, or 0. And on the other hand, you need to distinguish from a large number of possible regions. And it's not hard to show that there are, that for even generic configurations, the number of possible answers is, say, more than n over d to the d. And so just from sort of information theory, the fact that the set of answers to your queries needs to encode one of these regions, it needs to be the case that your algorithm needs to take omega of, well, the log of this, so d times log of n over d queries. And so the question is, well, there's a pretty big gap between these upper bounds and lower bounds. Where's the truth of the matter? What is the right answer here? And so there are some known bounds. So the lower bound from information theory, as far as I know, has not been improved. But at least if you think of the case where n is much, much larger than d, there has been substantial improvement on the upper bound. So Mazur in 1993 gave an upper bound of O of d to the 5th log n. This has since been improved a couple of times. And so there was a bound in 2016 that gave O of d squared log d log n. And so this is really the bound that we're trying to compete with. But the result that we prove is that the point location problem can be solved using an expected number of queries equal to O of d times log squared d times log n plus d times 2 to the O of square root log d. So a couple of things to note. The secondary term here, the second term that we have here, this is d to the 1 plus little o of 1. So for very large d, this is less than d to the 1.00001. So it's not too bad. And in fact, if n is very, very large, it's actually, goes away. And the second thing to note is that the first term is optimal. It matches the lower bound up to this log squared d factor. So the bound that we have is at least reasonably close to the optimum. Is there a question?
Yes, could you remind me what D is? I'm sorry, I missed that.
Right, D is the underlying dimension of the problem. N is the number of points in your pool slash the number of hyperplanes in your group.
Okay, that's clear, thanks.
Okay, so this is our result. There is a little bit of question about like what exactly you mean by classify. And so if you just want a classifier that works with probability, that should be with probability delta of errors. So with probability 1 minus delta, it classifies everything correctly. We know how to do that using just O of d log squared d log n over delta queries. So if you just want a high probability answer, this sort of annoying secondary term, we can dispense with it entirely. Okay, so those are the results that we're going to try and prove. And I guess, yeah.
Sorry to interrupt. Up until like that last slide, there was nothing probabilistic in the discussion. So I'm just wondering whether the probability is coming from some assumption on the data or the algorithm is random or.
Right. So the probabilistic statements there are entirely randomness used by the algorithm. And unfortunately, we don't know how to entirely de-randomize these algorithms yet. So the main theorem, it always gives the correct answer, but it needs to randomize which questions to ask, and if it gets unlucky with which ones it asks, the runtime might be long. We just have a bound on the expected runtime, and the other version actually has a probability of getting the wrong answer.
Great, thanks.
Okay, sure. So let's get into how this algorithm works. And the first thing that we're going to want to do is show how to learn high margin points. And this is actually sort of a very natural way to approach this problem. And the thing to note is that this problem is homogeneous in H and the xi's. I mean, all we care about is the sign of dot products of these things. And therefore, we can renormalize everything. We can normalize them so that, H and xi all, say, have L2 norm 1. They're all unit vectors. And a very natural approach to trying to learn, the dot products of H with xi's is just to try to approximate H. And it's not too hard to do this. For example, you can learn H to L2 error epsilon with something like O of d times log d over epsilon samples. And there are a lot of ways to do this. One easy way to do this is first find a coordinate I such that the absolute value of hi is maximal. And you can do this just by sort of comparing the absolute values of different coordinates. You can query to get the sign of hi plus or minus hk. This is really just h dotted with the vector ei plus or minus ek. And by making something like a linear number of such comparisons, you can determine which coordinate of H has the largest absolute value. Now, once you know that, you can, for each K, you can approximate the size of HK divided by HI to a tiny error. And the way we're going to do this is we're going to sort of do binary search. We're going to make queries that ask for the sign of HK minus alpha times HI for various values of alpha. And when we do that query, it'll basically tell us, is HK bigger than or less than alpha times HI? And so if we just do a binary search on alpha for every value of K, we can get good approximations to each HK. And so if we do something like log D over epsilon queries for each coordinate, we'll learn every coordinate to very good accuracy. And we need to do that D times to do it for every coordinate. So we need a total of something like D times log D over epsilon queries. Are there any questions about this?
Aren't all the H's going to be on the unit sphere?
All of the H's are on the unit sphere, yeah. We assume that they had that normalization.
So what does absolute value HI mean then?
Sorry, what? Oh, sorry. So here I'm using HI to mean the ith coordinate of the single hyperplane normal vector H.
Oh, okay.
So yeah. So this thing is, I'm in the active learning version of the problem. So there's just one hyperplane H. And here I'm using HI and HK to denote coordinates of that vector.
All right, thank you.
Okay, so here's what we have now. We know some, and I guess, this is maybe bad notation now. So some other vector H naught, where we know that the distance between H naught and H is at most epsilon. And in particular, since the x's we normalized to have norm 1, we know that the difference between H naught dot xi and H dot xi is at most epsilon. And in particular, this means that for any one of our points xi, if it were the case that H dot xi was more than 2 epsilon, then the fact that we know this epsilon approximation to the dot product is sufficient to learn the sign of H dot xi. And so in particular, we can learn the value of our function on all points where the margin, by which we mean the absolute value of this H dot xi, is large. And so in particular, for any sort of non-degenerate instance, we've already solved the problem. If the xi were random unit vectors, they should all have margin, approximately, they should all have margin at least something like 1 over n root d or something like that. And so with only O of d log n times d queries, we would just be done. We would just approximate H to really good accuracy, use that approximation to approximate all the dot products, and we'd be in good shape. Similarly, as was mentioned, if there's a separation between the positive examples and the negative examples, that basically says that these points have large margin. Under such an assumption, we can learn all the points in a pretty reasonable number of queries.
A couple questions.
Yeah.
Okay. Are we talking about the dual problem or the other problem?
Right.
Because I'm getting confused.
Right. So I'm talking about the active learning problem here for basically the rest of the talk. So there's a single hyperplane H, and there are a bunch of vectors xi, and I'm trying to learn the sign of all the signs of H dot xi.
Okay. And what does it mean xi are random?
So if my xi's were generated by picking uniform random unit vectors.
You can't do uniform random on the whole space.
Uniform random on the unit sphere.
But well, initially we're working with points in the whole space. So then you're normalizing them?
Right. So without loss of generality, you can normalize things so that all of the x's and the unknown hyperplane H are on the unit sphere.
Okay, that's going to change the density in some weird way.
I mean, it might change what you mean by random, potentially.
Right, if the
It-
density on the unit sphere is uniform, but then the transformed on the entire space is just, I don't know, 0 everywhere.
Well, I mean, yeah, there's not maybe a natural way to pick random points on RD.
Okay, thanks.
Sure. Okay. So yeah, so we've basically solved the problem if all of our points have reasonably large margin. So of course, the problem for us, basically the thing that we still have to answer is what happens if there are few or no large margin points? What if, there's this unknown hyperplane, but basically all of the points are clustered exponentially close to that hyperplane? I mean, we really want to solve this problem for any set of points. The points could be arbitrarily close. So we can't just assume that computing all the points with margin more than epsilon for really any epsilon is going to be sufficient. We need to come up with something more general. And so the second step is we're going to use this idea of a Forster transform to try and reduce to the case where we at least have some points of high margin. And the basic idea is, so we have this bad case where our points have low margin. And let's really think about the worst examples of this. What happens if literally all of our points have incredibly small margin? They're exponentially close to this unknown hyperplane. And so all of our points, they cluster really close to this hyperplane H. And basically there's sort of a problem that when we were trying to approximate the size of this normal vector, because all of our points are so close to this hyperplane, this H that we're trying to learn, the directions orthogonal to this hyperplane, even though they're very tiny, become very important to us. It matters a lot if we tilt the vector that we're trying to learn by just a tiny bit in any of those directions. That'll vastly affect which side of the hyperplane most of these points are on. On the other hand, our current algorithm sort of treats all directions equally and tries to just learn H up to some small L2 norm. And so we're trying to, somehow we need a metric that sort of better expresses the way that we need to learn things. And maybe another way of saying this is that we have all of these points that are clustered super close to the hyperplane, and somehow that's distorting the way that we're looking at things. And so what we want to do is we want a way to rescale it. And for just the case where you have a bunch of points that are super close to a hyperplane, you can literally rescale the points outwards. Basically, we're applying some linear transformation to our problem, but we're doing it in such a way that we're sort of getting rid of this weird issue that everything's clustered next to this hyperplane, which is leading to small margin, which is preventing our algorithm from working. So this is the sort of high-level idea of what we're trying to do. But to get down to some more details, the first thing that we need to ask is how do we rescale points while preserving the properties of the problem? We need a way to move points around while preserving half spaces. And a natural way to do this is by linear transformations. So if we replace every point x by ax for some, say, invertible matrix A, then h dot x becomes A inverse transpose h dot ax. And so the points where h dot x is positive and negative are now the points where A dot x dotted with this, somewhat different normal vector are positive and negative. And so exactly what the normal vector is has changed some, but the fact that the positive and negative points are separated by a half space, that's still preserved. We've sort of preserved the essential features of our problem. Now, we would also like to preserve the norms. norms. This fact that everything is unit norm is very convenient for us in doing things like defining margin in a useful way. And so what we're going to do is, after applying this linear transformation A, we are then going to renormalize all of our vectors. So we're going to define this function f sub A of x to be, you take, you apply A to x, and then you divide that vector by its norm. So you renormalize it so that everything's back on the unit sphere. And the nice thing to note about this is that this function f sub A, it still preserves half spaces, right? We first applied a linear transformation, which preserved half spaces, and then we rescaled things, which preserves half spaces. But this transformation does not preserve margins, because when you sort of rescale the points to put them back on the unit sphere, different points need to be rescaled by different amounts, and that will actually change the relative margins of these points. And so the hope is that by applying one of these transformations, we can go from a problem where almost all of the points have incredibly low margin to some problem where that's not the case, where a good number of our points have large margin. So the goal is to apply this transformation for some well-chosen value of A to make the margins good. And so the question that we need to ask ourselves when doing this, though, is how do we guarantee, after we've applied this transformation, that we have many high margin points? And this is a little bit tough, because what the margin of a point is depends on what this unknown separating half space is. And so we need a way to guarantee that no matter what the separating half space is, that a decent number of points still have large margin. And a very convenient way to do that is via isotropy. So we say that a set of unit vectors in Rd, x1 through xn, is isotropic if the sum of xi transpose is proportional to the identity matrix. Now, in particular, another way of looking at this is what it says is that if you have any unit vector v, the average value of v dot xi squared is going to be equal to 1 over d. And from this sort of equivalent way of looking at this, this implies that there's at least maybe I need to add some constants here to make this actually true, but it implies that something like at least a 1 over d fraction of the xi's need to have margin at least 1 over square root d. Because if you didn't have something like this, then the average value of h dot xi squared would be too small. And so in particular, if we can put our points in isotropic position, it guarantees that at least a reasonable number of these points have margin that's at least a reasonable amount. Okay, so what we want is we want to find a matrix A such that if we apply this transformation f sub A to our original set of points, we end up with a bunch of points in isotropic position. And somewhat conveniently for us, this turns out to be almost always possible. And so here's the proposition, and this sort of really builds on work of Forster from 2002, which says that if you're given any set of points in Rd, there exists a matrix A such that this set of Fa of xi is isotropic. This is true unless there is a k-dimensional subspace V for some k less than or equal to d that contains at least a k over d fraction of the points xi. Now, I will note that this exception for there being this sort of dense subspace, something along these lines is actually necessary. If you have a proper subspace that contains a large fraction of your points, then no matter what kind of linear transformation you perform in rescaling, it's still going to be the case that a low dimensional subspace contains a large fraction of your points. And if it contains too many points, then the directions along that subspace are going to, in general, have too much variance. Your points are going to have too much mass along those directions, and it won't be possible for them to be isotropic. However, you can show that this is really the only thing that can go wrong, the only thing that prevents you from finding one of these transforms. So we do, of course, need to deal with this exception. If there is a subspace with many, many points, well, we can maybe restrict to that subspace and try and find a Forster transform of that subspace. And that we can do unless there's a subspace with, again, too many points. And we can just repeat this. And so the corollary that we get is that if you have, give me any set X of points in RD, there is some k-dimensional subspace V that contains at least a k over d fraction of the points, and a matrix A such that the appropriate transform FA, when applied to the intersection of X with V, that set is isotropic, I guess, within the space A of V. And so you've got this subspace that contains a decent fraction of the points. After applying this transform, we're guaranteed that a decent fraction of those points now have large margin. And so in particular, after applying this transformation, we have a guarantee that at least a 1 over d fraction of the points have reasonably large margin. And in particular, this gives, yeah.
I had a quick question about that. So if the points are on the hyperplane, then even if you move them around inside the hyperplane, then they're still on that hyperplane. So you won't be able to have a high margin.
Right.
So I'm a little bit confused on how that works.
Right. I guess, yeah, this I guess does assume that you don't have points that are you don't have too many points that are exactly on the hyperplane.
Okay.
Yeah.
I have one more question.
Yeah.
I have one more question.
Sure.
So you had points in the beginning in the Euclidean space, and then you projected everybody to the unit sphere. But then it could happen that everybody gets projected to the unit sphere at the same point.
It could be the case in theory that multiple points get mapped to the same point when you map them to the unit sphere. But this will only make our lives easier, because if 2 points are multiples of each other, then the sign of h.x1 and h.x2 have to be the same.
Yeah, but there is a problem because some of these points on the same line could be green and some others will be red, and then
well, no. So because we assume that the separating half plane was homogeneous, that it passes through the origin. And so that means that if 2 points are on the same ray coming out of the origin, they have to be on the same side of the half space.
Oh, okay. Okay, so there were a lot of assumptions involved in this anyway. Okay, thank you.
Well, yeah. So well, I mean, remember, we can sort of, by adding an extra dimension, force things to be homogeneous. We can force the hyperplane to pass through the origin by adding an extra dimension to the problem.
Yeah, this looks like a support vector machine idea, but okay. All right, thank you.
Sure. Okay, and so this actually gives us sort of our first algorithm. So what we're going to do is we're going to apply this Forster transform on a subspace. And then we know that we can approximate H, and this learns the high margin points. And we know that that was actually a decent fraction of our total points. And then what we can do is we can just repeat on the remaining points. And so the point is that after we've learned the high margin points, it might be the case that the points that we haven't learned yet, those are all super low margin. And so what we would need to do is we would need to reapply a Forster transform to put them back into isotropic position. Then in this new set of coordinates, we need to relearn the orthogonal vector, and then that learns us some new points, and we can keep iterating this. And the point is that each iteration needs to use O of d log d queries, and it learns in total at least a 1 over d fraction of the points. It learns the signs of a 1 over d fraction of the points. And so the total number of iterations that we get here is O of d log n in order to learn all of the points. And so the total query complexity of this algorithm is going to be O of d squared log d log n. And this is okay. unfortunately, I mean, this d squared, it's comparable to the previous algorithms that were known. So if we would like to get something, closer to the optimum lower bound, we do need something better. But at very least, we now have an algorithm that works for arbitrary point sets and isn't super bad. Any questions about this? Okay, so what's the next step? The next step is to try and get some sort of understanding of the margin structure. And so sort of the bad case that we're looking at is what happens if we have many, many, many low margin points. And what we're going to do is let's assume that we've already put these points in isotropic position. So at least a few of them are high margin. But maybe it's the case that all but a k over d fraction of the points are extremely low margin, and the rest of them are high margin. So we've got this instance where we've got our hyperplane. There are a ton of points that are basically smack dab on the hyperplane, and a small fraction of the points are high margin. And the point is, our old algorithm said we're going to use a d log d samples to learn this k over d fraction of the points. But if you keep doing that, you really need something like d squared samples. That's not good enough. We want a way to learn these high margin points more efficiently. And one interesting thing is what happens when you look at these low margin points. And in particular, if you look at this sort of average of XX transpose over those points, it's a positive semi-definite matrix. It's trace 1 because they're all unit vectors. Each XX transpose has trace 1. And because the average of this over all of our points is 1 over d times the identity, and because these low margin points are almost all of our points, you can show that the eigenvalues of just this average over the low margin points are bounded above by something like 1 over d minus k. And what this means for us in particular is that you actually need to have a lot of large eigenvalues. The span of these low margin points must be some subspace V of dimension at least d minus k. And what's the point of this? Well, if we knew what this subspace V of low margin points were, we would know that there's this high dimensional subspace V that is almost orthogonal to this unknown hyperplane, or this unknown vector H. And so in particular, if we took all of our high margin points and projected them onto V perp, this would do basically nothing to change which side of the hyperplane they're on. But on the other hand, I mean, V perp is a much lower dimensional space. So, and maybe more formally, we know that for every point in V, because it's a span in the span of these low margin points, H dot V is very, very close to 0. And so that says that H dot X is very, very close to H dot, the projection of X onto V perp. And in particular, this means that if X was already high margin, the sign of H dot X should be the same as the sign of H dot, the projection of X. And where does this gain us something? The advantage that we have here is that V perp was only k-dimensional. So if we only need to estimate H along these directions in V perp, we can do that in k log k queries rather than d log d queries. And so what do we really need to make this work? So we need a set of high margin points H and a set of low margin points L. And I want the set of low margin points L to be very big. I want it to be like size of X minus twice size of H. So I don't quite need it to be every point is in one or the other, but I do need that like it's almost that good. And thirdly, I really need there to be a gap in the margins. I want it to be, for example, that the smallest margin of any point in H is at least d to the 10 times bigger than the largest margin in L. And I sort of need this because when I'm arguing that points in V are low margin, really what I'm saying is I'm taking a point in V and I'm writing it as a linear combination of these low margin points. But if I need to use somewhat large coefficients, in that linear combination, I might lose polynomial and d factors. So I want to make sure that even after doing this, there's still much lower margin than anything else. And so, well, suppose that we could find such high and low margin point sets. Suppose that the size of h were something like k over d times the size of x, then we can learn a k over d fraction of all of the points in something like k log k queries. And in particular, if we just keep on repeating this until, say, the sum of all the k's that we have used is, say, d, then over that time we've used something like d log d queries, and we've learned a constant fraction of our points. And then if we keep repeating this until we learn all of our points, we've only used something like d log n queries. And so if we can really do one of these things where we learn a k over d fraction of the points in k log k queries, then by just repeating this sort of thing as a black box, we've got a good algorithm. We've got an algorithm that in approximately d log n queries learns everything. Now, of course, in order to get this to work, there has to be a drop. There has to be an actual place where it can split to high margin and low margin, where the drop is pretty substantial. And to think about this, let's let f of t be the margin of the sort of t times size of x highest margin point. And what we need is we need a value of t such that f of t is bigger than d to the 10 times f of 2t, where if you look at twice as many points, the margin is smaller by a giant factor. So we need f to have a big drop. If we graph f, it's this decreasing function. We need there to be a point where the value of f drops quite rapidly. On the other hand, existentially, it's not hard to show that such a drop exists. If the points in x are in isotropic position, either it is the case that all the points have margin more than d to the minus log d or so, or there is some value t such that f of t is bigger than d to the 10 times f of 2t. And the proof of this is pretty simple. I mean, by isotropy, we know that f of 1 in d is bigger than or equal to 1 in d or something like that. And if it were the case that for all t, f of 2t was bigger than f of t times d to the minus 10, then we'd have that f of 2 over d is bigger than d to the minus 11, f of 4 over d is bigger than d to the minus 21, so on and so forth. We repeat this log d many times, and we find that f of 1 is bigger than d to the minus o of log d. So either there's one of these places we have a big drop, or all of the points have reasonably large margin. Okay, so this is sort of what we're looking for. But in order for any of this to work, we need an algorithm to actually find these subsets, H and L. And the problem is that we can only afford to use k queries. The idea is that we wanted to use k queries to learn a k over d fraction of the points. If we're willing to use d queries for it, it doesn't help us very much. And, well, so let's simplify things a little bit here. Actually, it suffices to find only something like approximately d many random low margin points. And this is because you can show that if you have approximately d many random low margin points, they will have approximately the same span as the set of all the low margin points. From that set of points, you can compute v, just as you would before. And you project all the other points onto v perp, you estimate the projection of h onto v perp, and by just looking at the dot product of this projection of h with the projections of your other points, you can identify which of the points are high margin. Like if that dot product is large, then you successfully learn the signs of those points. So the goal is just we want to first sort of know where there's a gap between high and low margin points, and then we want to find about d random low margin points. And unfortunately, there's still not enough queries to do this, in part just like if we want to find d points and we need to verify that they are all low margin, that if we actually want to be sure of our answers, it's going to require D queries. And so what we're going to need to do is we're going to need to find some way to screen many points at once. And the basic tool that we came up with is we want what we're going to call a margin oracle. What this does is it takes a set S of points and it returns a point X sub S so that the absolute value of H dot X sub S is approximately the same as the maximum over X in this set of H dot X. So it's a point that sort of is representative of approximately the highest margin point in this set. And this will allow us to at least test. If we have a large collection of points, it will allow us to test if any of them have large margin. And the nice thing is that if you're willing to use some randomization, there is actually a good random implementation of this margin oracle. And it's actually very simple. We're going to let X sub S be a random Gaussian linear combination of the points in S. And the point is that if you look at H dot X, this is a Gaussian random variable. And the variance of that Gaussian is the sum of the H dot Xi's squared, which is on the same order as the maximum of the H dot Xi squared. And so this very simple randomized oracle with, good probability gives us some point that's probably representative of the highest margin point in our set. Okay, so we have this oracle. Next thing that we want to do is we want to find structure. We want to find a place where there's a big drop in the margins of points. We've got K over D fraction of points with high margin, and almost all of the rest of the points have much lower margin. And the way we're going to do this is we're going to take M to be various powers of 2. And we're going to take random sets S of size M and random sets T of size 2M and ask, is it typical that H dot, this sort of margin oracle point for T, is bigger than D to the 10 times H dot, the representative point for S? And if this is true, since these points in T often have very large margin, this means that about a 1 in M fraction of the points have large margin. But because this set of only M points often has much smaller margin, it also has to be the case that except for an O of 1 over M fraction of points, everything should have low margin. And so if we have an M for which this kind of gap is typical, it's not hard to show that you can find an appropriate gap between high margin points and low margin points that happens at this scale. And in particular, we will have the type of structure that we are looking for with a value of K that's approximately equal to D over M. Now, once we know where the structure is, we still need to find approximately D random low margin points. However, with this margin oracle, there's a reasonably easy way to do that. If you take a random set of M points, this will have a constant probability of all the points in that set being low margin. And we can actually check to see whether this is the case with a single sort of call to our margin oracle and a single comparison. And so what we're going to do is just O of K many times. We're going to pick these random sets and check which ones are low margin. And then we're just going to keep on, about half of them will be low margin. We put all of those together, and that gives us our approximately D many low margin points. So in summary, what do? We apply the Forster transform, or possibly apply the Forster transform to a dense subspace. We then do these sort of tests for various M's powers of 2 to find this threshold where we think there's a big gap between high and low margins. We then, using this oracle and taking another bunch of random samples, we find approximately D many low margin points. Then we use those low margin points, find their span to get this subspace V. We approximate the projection of H onto V perp, and then we use the fact that these points spanning V were low margin and the fact that we've got a good approximation of the projection of H onto V perp to infer the values of the high margin points. Now, and once we've done that, we've inferred a bunch of points. We repeat this on the remaining points. We apply a new Forster transform, and so on and so forth. Now, there is a problem with this algorithm. And one way of saying, if you want an algorithm that never never comes to a wrong conclusion, what we have here doesn't actually achieve that. And the problem is when you collect this set of D low margin points, we were having to use the margin oracle to do that. And the margin oracle is not guaranteed to be correct. And so maybe we got unlucky, and even though there were some high margin points in our set, our margin oracle still returned something of very low margin. And
on that point, is there an assumption you could say about the points such that your Gaussian approximation is true? Like maybe for some distribution for the X points, the Gaussian is true, and for some others it doesn't work well.
Well, I don't think there's going to be any condition on the points that do this, because no matter what set of points you give me, the margin of this Gaussian random linear combination of them is going to be a Gaussian. Now, the variance of that Gaussian is going to be proportional to the highest margin, more or less. But I mean, if you give me a sample from a random Gaussian, if I get unlucky, I might always get a point that's much, much smaller in absolute value, or much, much larger if I'm super unlucky than the standard deviation.
I'm not saying the X points are necessarily Gaussian, but they might have some specific distribution such that your oracle is the correct distribution.
I mean, if you're running the oracle the way I said, which is take an actual random Gaussian linear combination, then any set of X points, I could always get unlucky and pick the wrong linear combination, so that...
That's true. So I guess I'm talking about expectation.
I mean, so in expectation, things are always fine, right? It's always the case that, the margin oracle works with, I mean, depending on what you mean by work, depending on sort of how bad your approximation needs to be, but it always works with high probability.
Okay.
And that's true no matter what your set of X points are, but it only ever works with high probability. There's always some potentially tiny chance that it gives you the wrong answer.
Right, thanks.
Sure. And so if you want to guarantee that you get the right answer, there's this problem that there might have been points that my oracle told me were low margin, even though they actually weren't. And unfortunately, if I actually have a set of points and need to verify that all of those points are low margin, there really isn't a better way to do it than really doing at least D queries, or querying all of the points or something like that. And so the final step, if you want to get an algorithm that never makes errors, we need to find a way to do verification. We need to verify that these low margin points were actually low margin. And I guess I'm actually running a little bit over, so I'll try and do this quickly. But so the above algorithm, it probably works, but if you want something that doesn't make mistakes, you need to deal with this fact that these purported low margin points might not actually be low margin. And to just briefly, review how the algorithm works, round one, it produces some low margin points and some high margin points. And we can actually literally conclude that if these low margin points all have much lower margin than the high margin points, we can infer the high margin points. And so we do that, and then we do it again, and then we do it again. And one thing to note about what happened here is that the actual margins of the points change from round to round, because between rounds we applied a Forster transform, and these changed the margins of all the points, but it at least changed them in a particular way, in a predictable way. It just multiplied them by some known constants. And the thing that we need to do is we need to verify that in each round, every point in HI has much larger margin than every point in the corresponding LI that we used. And there's one more thing that we get. If the inference works, then not only did we learn the points in HI, not only did we learn their sign, but we learned their approximate margin. And well, because margins change round to round, really we can say that we learned approximations to the relative margins of all of those points in HI. And so here's a way to set up the thing that you need to do to verify that all of these inferences were correct. So for each set HI, I can select a representative point Xi. And if I want to verify that the ith round was inferred correctly, I need to verify that this margin h dot xi is bigger than some cy times the margin h dot yi for some of these uninferred points yi, these points yi that were in this set L of low margin points. Now, of course, these yi's in later rounds, we eventually inferred them correctly. And when we inferred them, we also related their margin to the margin of the representative point of that round. And so really all that we need to do is for every pair of representatives, we need to verify some relation that the margin of xi is at least some constant cik times the margin of xk. And so what we have is what we call a matrix verification problem. So if we have R rounds, there are different xi's, and there's this whole matrix of CIKs, and we need to, verify these inequalities about the margins. We need to say something about the relative margins of just these representative points. And what's cool is that this matrix verification problem is just another point location problem that we could solve. It's got, R squared comparisons in D dimensions that we need to verify. Unfortunately, R squared is going to be something like D squared log D or something like that, or log D squared. And this problem might be worse than the problem that we started with. And so we can't just recursively run our learning algorithm to make this work because our recursion doesn't simplify things out. But we can do it if we're slightly more clever. And what we're going to do is we're going to split all of these representative points. We're going to split them into m equal groups. And what we need to do is we need to show that each h dot xi is bigger than the maximum of CIK times these margins h dot xk. Now, for each group I and each group, we're going to find the biggest term in that maximum where k lies in that group. And we note that if you fix a group and want to find, for each I, which one of these terms in that row is the biggest, that's a point location problem. Now, there are actually m of these because we need to do one problem for each group. But these problems are in only R over m dimensions because there are only R over m many x's in that group. So there are R over m dimensions. There are something like R times m squared many planes that we need to figure out which side we're on. But that's actually okay. And once we've done that, once we have sort of the biggest term in each group, each h dot xi only needs to be compared to the maximums in each group. So a total of something like R times m additional queries. And so in the long run, we get this recursion. To solve a d-dimensional n-plane point location problem, we need O of d log squared d log n samples, and we need to solve an O of d log n sized matrix verification problem. To solve a size R matrix verification problem, we need to solve m different R over m dimensional Rm squared plane point location problems, and then use R over O of R times m additional queries. And I don't want to get into the details, we're already a bit over, but if you apply these recursions cleverly, at least when n is only polynomial in D, you get our answer. You solve the point location problem in O of d log squared d log n plus d times this 2 to the O of square root log d queries. And you can also make this work for larger n once you've solved it for smaller n and then use some extra tricks. Okay, so what's the conclusion here? There was this lower bound, d log n over d. The previous best upper bound algorithm did d squared log d log n. Our algorithm, it has two terms, this O of d log squared d log n, which is optimal up to log factors, plus this extra term d times 2 to the O of square root log d, which is d to the 1 plus little o. There are some open problems left. One is to de-randomize. So even the the version that does verification, still the runtime is only expected. If we keep getting unlucky with these margin oracles, our verification step will determine that we got the wrong answer and try again. But if we keep getting unlucky, we might have to try again over and over and over again. And so we might have to spend an unlimited number of samples. It'd be nice if we could de-randomize this and have a guaranteed bound on the number of samples, number of queries. Another thing to do is try and make things actually optimal. There's this log factor that in the main term that would be nice to get rid of. There's also this d to the 1 plus little o. One term that would be good to get rid of. Another thing that you might want to do is to try and see if it's possible to do this with simple queries. The oracle queries that we use are a bit of a mess. They require taking sort of random Gaussian linear combinations of reasonably large subsets of points. It'd be nice to know if you could use only queries that were like linear combinations of 2 or 3 points or something like that. But yeah, that's all I had to say. Are there any questions?
Thanks, Danny. That was really cool. I think we have time for 1 or 2 questions if people want to hang around, and as long as Daniel is fine, we can keep going, but I'm going to stop the recording.